the two-wire transmission line has Z0 equal to 50 ohms, operated at 3 gigahertz, with load value 100 plus J40. So the question A, find impedance at a point which is 2.5 centimeters from the load. Okay, and next part B question, find VSWR. Okay, so this is a question. Anyway, first let me bring up the Smith chart. All right, so they have given the details such as the Z naught and load impedance. So let's convert the load impedance. Right? So that is ZL, small ZL is equal to the capital ZL divided by Z. How much is that? We have 100 plus J40 by 50. Correct? So that is 2 8. So 2 plus J 0.8 ohm. This is what I am supposed to mark on this. Okay. So let's mark this particular point. 2 plus J 0.8 on this Smith chart. So I can see 2 here, and I want to mark 0.8, right? So 0.8 is 0.8 is this line with the 2. I think this is the point. Okay, just verify. So this is the ZL. As soon as I mark this, normally we will connect the point to the origin and extend the line passing through that. Right, and we'll try to read the location, and we'll try to read this location, right? So 0.21246, it's between 6 and 7, 6 and 8 for me. So maybe, right? Just give me your value. I'll write that value here. So that this value is, how much is that value? Please tell me. Okay, I'll write. I think 0.21, maybe it's a 6 or 8, I guess. Just check and tell me. Okay, 216, right? Okay, 216 lambda. Fine. So anyway, we got that. Now, corresponding to the distance of what you call 2.5 centimeter. Okay, I have to check what is the distance I'm supposed to travel, because everything is in terms of lambda, right? So first let me find out lambda. So what is the lambda? Lambda is equal to C by F, correct? So C is 3 into 10 to the 8 divided by the frequency is given. If you see, what is the frequency of operation? 3 gigahertz. 3 into 10 to the power 9, correct? So the lambda is equal to 3 cancels. It is simply 10 to the minus 1 meters, right? Or I can write 1 by 10 of a meter is a 10 centimeter, correct? Now the distance I am supposed to travel is 2.5 centimeter, correct? So just see the question. Find the impedance at 2.5 centimeter from the load. Now I need to represent the 2.5 centimeter in terms of lambda. Okay, so you simply use this. See, if it is 10 centimeters, this is corresponds to lambda. Okay, 10 centimeter is 1 lambda. Now my question is 2.5 centimeter is equal to how much lambda I want. Is it okay? So that is equal to, right, corresponding to 2.5 centimeter, it is 2.5 into lambda divided by 10. Centimeter cancel, so this is equal to lambda by 4, correct? So lambda by 4 is 0.25 lambda is what I am supposed to move, right? So this is the distance that you need to cover towards generator. So towards generator, it's not a question. Are you fine with this? Okay, now see that you have a value equal to 0.216 lambda plus 0.25. This implies your new distance is equal to 0.216 lambda plus 0.25 lambda, right? So the new value becomes equal to 0. This is 4, correct? 466 lambda. Is it fine? Okay. So mark that 0.466 lambda on the graph. Okay, so 0.466 lambda is 46, 462, 464, 466 is this point, correct? Okay, again I'm using the outer scale because I'm moving towards the generator, right? So connect the origin, connect the origin to that. Okay, so that is origin. So this value is now how much? 0.466 lambda. So what's the impedance is the question. So draw a circle like this and reach this point. So the new point what you measure here is the Z1. Okay. So the Z1 value is, this is what you are getting. Okay, I'll write here on the graph itself. Okay, so Z1 equal to 0.34. All right, then so the value may change. Practical value might change because whatever I have marked is not to the scale. When you draw exactly taking, yeah, approximate X value R, right? So 0.34, correct. Then I have a minus because it is below the horizontal axis, minus J. According to my graph, it is 0.2, correct? But definitely it will change when you do it practically. Practical value will be different. Okay, so that implies I'll calculate the Z value. Z is equal to, as we got, 0.34 minus J 0.2 should be multiplied with the Z naught value. So in this case, what is the Z naught value? Z naught is 50. Okay, convert that, 0.34 into 50, 17, minus J, uh, that will be, no, 0.2 into 50, correct? That's what you are doing. Ah, no, it's zero point 0.2 into 5, so 10, right? So I guess you should get a 10. 0.2 into 5, 10 times, right? So 10. Oops. Okay, so that's the first part. Then look at the second question. Find the voltage standing wave ratio. What you are going to do, you will keep the same radius and measure that on the scale, first scale, right? First scale, right? We may measure a value, something like this, maybe. So that will be the VSWR. All right. Now, next I'll give you a homework question. You try to solve, okay, on a proper Smith chart, and we'll verify the answer later, okay, when we discuss this, right? So this is the next question. A line is 3 lambda by 8 long with normalized input impedance equal to minus J 2.5 ohms. Okay, part A of the question. Find the normalized load impedance. That's part A of the question. Part B of the question, find distance first voltage minimum from the load. Okay. And part C of the question, find the length of the open circuit line required to replace the ZL. Okay, so that is the question. We totally have three parts in this question, and you try to answer them using the Smith chart. We have to solve this using the Smith chart. Okay, once you get an answer, right, when we meet next time, we will discuss how the actual answers. Okay, we'll compare the answers and then we'll proceed further.